Today, our study focuses on how different light wavelengths affect how human skin looks and reflects light. Skin appearance is strongly influenced by lighting, which is why this topic is important in areas such as photography, cosmetology, dermatology, and visual technology. While the effects of ultraviolet or UV light on skin damage are already well known, the impact of visible light has received much less attention. Visible light is the part of the electromagnetic spectrum that we can see, ranging from about 380 to 780 nanometers. In this study, we compare short wavelengths like blue light, medium wavelengths like green light, and long wavelengths like red light. Different colors of light interact differently with skin pigments such as melanin and hemoglobin. Because of this, the same skin tone can appear lighter, darker, warmer, or cooler depending on the light source. Our study measures how much light is reflected from the skin at different wavelengths and examines how this affects skin tone perception. Research shows that longer wavelengths, especially above 590 nanometers, can penetrate deeper into the skin, and aging skin reflects light differently. The results indicate that darker skin reflects less light than lighter skin, especially at wavelengths around 460 and 570 nanometers. This happens because melanin absorbs more light. As a result, lighting conditions can significantly change how skin tone is perceived, which darker skin may appear less vibrant, while lighter skin may appear brighter. Overall, the study highlights the importance of understanding how visible light affects skin appearance, especially for medical, cosmetic, and imaging applications. Skin looks different under different types of light. For example, red, green, and blue light can change how a person's skin tone appears. However, we do not fully understand why this happens. One possible reason is that skin reflects different amounts of light at different wavelengths. This becomes a problem in areas like UV lighting, skincare analysis, and photography, where showing skin accurately is important. Poor lighting can make skin look unnatural or misleading. Because of this, our study aims to measure and compare how much light the skin reflects under different colors of light. The experiment was done indoors using control lighting. Use blue, green, red, and white light, and keep the distance, background, and skin condition the same to avoid interference. By comparing the reflected light, we hope to better understand how different light colors affect how skin tone is seen. For the hypothesis, we believe that longer wavelengths, which is red light, will have higher reflections due to deeper penetration and lower scattering, making skin appear warmer and brighter. Meanwhile, shorter wavelengths, which are blue and green light, will be more absorbed and scattered, giving a cooler appearance. This table shows the reflection coefficient of red, green, blue, and white light without using any skin sample. White light is used as a control, and its reflection coefficient is set to 1. From the results, red light has the highest reflective intensity with an average of 418.33 lux, giving a reflection coefficient of 0.83. Green light reflects less light with an average intensity of 347.67 lux and a reflection coefficient of 0.69. Blue light shows the lowest reflection with an average intensity of 266.67 lux and a reflection coefficient of 0.53. Overall, without skin, longer wavelengths reflect more light, while shorter wavelengths reflect less light. This table shows the reflection coefficient of the light reflected from human skin samples. The individuals were tested with different skin tones. Arisa has a fair skin, Bella has a medium skin tone, and Damia has a darker skin tone. White light is used as a reference, so the reflection coefficient for white light is 1 for all skin samples. The results show that Arisa consistently has the highest reflective intensity, followed by Laila and then Damia. This indicates that fairer skin reflects more light, while darker skin absorbs more light. For all three skin tones, red and green light reflects the most, and blue light reflects the least. In conclusion, we could see that skin reduces light reflection, and both skin tone and light wavelength affect the amount of reflected light.
Next, I will discuss the literature review that related to this study. This study focused on how light wavelength affect the appearance and perceptions of human skin. Previous research shows that skin appearance is strongly influenced by the interactions between light and skin tissue, especially the wavelength of the incidence light. According to Puran et al., human skin is affected by both ultraviolet radiations and visible light emitted from sources such as sunlight, electronic devices, and LED lights. Their findings show that blue light, which is a shorter visible wavelength, can accelerate skin aging, while longer wavelengths such as yellow and red light may have protective effects on the skin. In addition, He et al. Reported that skin reflects and absorbs light differently depending on skin pigmentations and the wavelength of light. Visible light in the 400 to 700 nanometers range interact with skin chromophores such as melanin and hemoglobin, which affect how much light is reflected and how skin is perceived. Supporting this, Beshkatov et al. Explained that shorter wavelengths are absorbed more strongly by melanin, while longer wavelength penetrates deeper into the skin layers. This explains why lighter and darker skin tones reflect different amount of light at certain wavelengths. Furthermore, Pesate used a GPU-accelerated Monte Carlo model to study the relationship between skin optical properties and aging. The study found that light with wavelength above 590 nanometers penetrates deeper into the skin. As skin ages, deeper layers scattered orange to red light differently, leading to visible changes in skin color. The study also shows that skincare products can improve this effect in a way that is noticeable to the human eye. Apart from that, Vata et al. Found that the source of light plays an important role in how skin tone is perceived, as skin reflections influence how it appears an image and to the human eye. Similarly, Will et al. Reported that uneven or uncontrolled lighting can lead to errors when judging the skin tone, especially in medical and technology-based studies. Therefore, using controlled and consistent lighting is essential when studying skin tone perceptions. Moving to the methodology part of this study, these are the materials needed to succeed this experiment, such as LED white light, red, blue and green filter, smartphone, neutral grey background, light intensity sensor, which is lux meter and skin sample. So, these are the procedures of this experiment. First, the experiment was conducted indoors to minimize the influence of external light sources. Second, a neutral grey background was placed behind the skin samples to prevent color interference. Third, the skin surface was cleaned and ensured to be free from makeup, lotions or oil. Fourth, the LED light source was positioned at a fixed distance from the skin surface. Fifth, the blue filter was switched on to illuminate the skin surface. Sixth, an image of the skin under the blue filter was captured using a smartphone camera. 7. The reflected light intensity is measured using a light sensor application. Next, the same procedures was repeated using red and green filter. Next, white light was then used as the reference light source, then image and reflection data are recorded. Then, the distance between the light source, camera, and skin was maintained constant throughout the experiment. Lastly, all captured image and recorded data were compared to analyze the effect of different wavelengths on skin tone perceptions and reflections.
This experiment was conducted to investigate the effect of light wavelength on reflected intensity, both with and without the presence of the human skin. Overall, the results show that reflected intensity varies with the wavelength and is strongly influenced by the optical properties of the skin. Referring to the measurements without skin, as shown in the result, white light produced the highest average reflected intensity at 505 lux and was used as the reference. Among the monochromatic lights, red light showed the highest reflection coefficient with R equals to 0.83, followed by green light with R equals to 0.69, while blue light recorded the lowest reflection coefficient at R equals to 0.53. This trend indicates that longer the wavelengths experience less scattering and are reflected more efficiently from a neutral surface, as reported by Austin in 2021. When skin samples were introduced, a noticeable reduction in reflected intensity was observed for all the wavelengths. This reduction can be attributed to absorption by skin chromophores, particularly melanin and hemoglobin, as explained by Joubert and Nidwani in 2025. Under white light, ISA recorded the highest average reflected intensity at 246.33 lux, followed by Lila at 201.67 lux and Damia at 144.0 lux, suggesting the differences in melanin concentration among the skin samples. Interestingly, for all three subjects, green light consistently produced higher reflected intensity than red light. Under green illumination, the reflection coefficients range from 0.23 to 0.25, while under red light, they range from 0.16 to 0.19. This occurs because red light penetrates deeper and is absorbed by deeper tissues, whereas green light undergoes stronger backscattering in the upper skin layers, resulting in higher surface reflection, as discussed by Wang in 2023. Additionally, hemoglobin absorbs strongly in the green region, enhancing surface reflection and making green light appear brighter on the skin, as reported by Yakimov and al. in 2024. Finally, blue light showed the lowest reflection for all samples due to the strong absorption and scattering, causing the skin to appear darker. Alright, so for the conclusion, the reflected ray without skin samples shows that white light produces the highest reflected intensity, which is 505 lux, followed by red, which is 418.33 lux, and green 347.67 lux, and blue light 266.67 lux, while for reflected ray from skin samples, the reading shows that with skin, green light showed higher reflected intensity than red light for all samples, with reflection coefficients ranging from 0.23 until 0.25 for green and 0.16 and until 0.19 for red. Blue light recorded the lowest reflection for all skin samples, which are R is equal to 0.11 until 0.14. These results confirm that skin reflection is strongly wavelength dependent, with shorter wavelengths being more absorbed and white light providing the most balanced reference.